Right now, at this very moment, billions of tiny water droplets are dancing in the sky above you, suspended in an invisible ballet that has been choreographed by the very breath of our planet. Everything you see when you look up at clouds isn't quite what you think it is. Those soft, pillowy shapes are actually intricate sculptures carved by forces so gentle and persistent that they reshape our world one whisper at a time. Welcome to Sleep About Science. Tonight, we're exploring the quiet miracle of how clouds form and move across our skies. And if you drift off to sleep while listening, that's perfectly wonderful. Your dreams might just be filled with the soft dance of water vapor and wind. Before we begin, please make yourself comfortable. Pull up your blankets, settle into your favorite position, and let your breathing slow and deepen. And remember, this is educational content designed to help you relax. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into the science that surrounds us every day. Now let's begin our peaceful exploration of the clouds above us. Imagine, if you will, that you could shrink yourself down to the size of a water molecule. You'd find yourself in a world of constant, gentle motion, where invisible forces guide your every movement. This is where our story begins. Not in the sky, but right here at the surface of our planet, where every drop of water in every ocean, lake and puddle is quietly preparing for its journey upward. Water evaporation happens so slowly, so gently that we rarely notice it. Each molecule needs just enough energy from the sun's warmth to break free from its liquid companions and float upward as invisible water vapor. It's like watching the most patient dance imaginable, molecules slowly gathering enough energy to lift off one by one, in a process so gradual it's almost meditative to contemplate. The air around us is always carrying some of this invisible moisture. Even in the driest desert, water molecules drift and dance in the atmosphere, waiting for their moment to come together again. Scientists measure this hidden moisture as humidity, but you can think of it simply as the sky's thirst, its capacity to hold these wandering water molecules in invisible embrace. As warm, moist air begins to rise, something beautiful starts to happen. The higher it climbs, the cooler it becomes, like ascending a gentle mountain where each step brings you into slightly thinner, slightly cooler air. This cooling happens at a predictable rate, about 2 degrees Celsius for every 1,000 feet of altitude. It's one of those quietly reliable patterns that nature follows, as steady and comforting as a heartbeat. But here's where the magic truly begins. As that rising air cools, it reaches a special point called the dew point, the temperature at which the air becomes saturated with all the moisture it can possibly hold. Think of it like a sponge that's absorbed all the water it can manage. Any additional cooling, and something has to give. When air reaches this saturation point and continues to cool even slightly, the invisible water vapor begins to transform. But it can't just spontaneously become visible droplets. It needs something to cling to, like a shy person needing a friend's hand to enter a crowded room. These helpers are called condensation nuclei, and they're everywhere around us, floating invisibly in the air. These condensation nuclei are wonderfully diverse, minus tiny particles of salt blown up from ocean waves, microscopic dust from distant deserts, pollen from flowers, even tiny fragments from meteors that have burned up in our atmosphere. Each one is smaller than you could possibly imagine, yet each serves as a perfect gathering point for water molecules to cluster around. The process of condensation happens with such gentle grace. Water vapor molecules, moving in their constant dance, begin to slow down as they cool. They start to cluster around these tiny particles, forming droplets so small that millions could fit on the head of a pin. These newborn cloud droplets are incredibly tiny, but typically only about 10 to 20 micrometers across. To put that in perspective, a human hair is about 5,000 micrometers wide. Once these microscopic droplets form, they don't simply fall. They're so small and light that the gentlest air currents keep them suspended, floating like dust motes in a sunbeam. The air molecules around them are constantly bumping into them, providing just enough upward force to counteract gravity's downward pull. It's a perfect balance, a delicate dance between falling and floating. Different types of clouds form at different altitudes, each with its own personality and character. The lowest clouds, called stratus clouds, form like soft blankets spread across the sky. They typically develop between the surface and about 6,000 feet up, creating those overcast days when the whole world seems wrapped in a gentle grey embrace. Cumulus clouds, those puffy cotton ball formations that children love to see shapes in, form when pockets of warm, moist air rise through cooler air around them. They're like gentle bubbles of moisture, each one marking a spot where the earth below has warmed the air just enough to send it climbing skyward. These clouds can grow throughout the day as the sun continues to heat the ground beneath them. Higher up, between 20,000 and 40,000 feet, cirrus clouds paint delicate brushstrokes across the sky. These wispy, feathery formations are made not of water droplets, but of tiny ice crystals. At that altitude, the air is so cold that water skips the droplet stage entirely and crystallizes directly from vapor to ice. These ice crystals catch and scatter sunlight in ways that create some of the most beautiful displays in our sky. The movement of clouds follows patterns that are both predictable and endlessly variable, like music that follows basic rules but creates infinite melodies. At the most fundamental level, clouds move because air moves, and air moves because of differences in pressure and temperature across our planet's surface. Think of the atmosphere as a vast ocean of air, with currents and streams flowing in 3 dimensions. Just as rivers flow from high ground to low ground, air flows from areas of high pressure to areas of low pressure. The sun's uneven heating of Earth's surface creates these pressure differences, warm air rising over sun-baked land, cooler air sinking over shaded areas or cooler water. The rotation of our planet adds another layer of complexity to cloud movement through something called the Coriolis effect. As clouds travel across Earth's surface, the planet's rotation causes them to curve slightly minus to the right in the northern hemisphere and to the left in the southern hemisphere. It's subtle, but it's part of what creates the great spiraling patterns we see in weather systems. At different altitudes, winds blow in different directions and at different speeds. Near the surface, friction with the ground slows air movement and creates turbulence. Higher up, air flows more smoothly and often much faster. The jet streams, rivers of fast-moving air between 30,000 and 40,000 feet high, can push clouds along at speeds of over 100 miles per hour. But clouds don't just passively ride these air currents. They also help create them. As water vapor condenses to form cloud droplets, it releases heat energy that was stored when the water originally evaporated. This released energy warms the air around the forming cloud, causing it to rise even more vigorously. It's a beautiful feedback loop. Nike's clouds creating the very conditions that help them grow and move. Within a single cloud, air moves in complex patterns of rising and sinking. In cumulus clouds, warm air rises through the center while cooler air sinks along the edges. This creates a gentle circulation pattern, like a slow-motion thermal spring that can keep clouds growing and evolving for hours. The life cycle of a cloud is a story of constant transformation. Clouds are born when conditions are just right for condensation. They mature as they gather more moisture and grow larger, and they eventually dissipate when the conditions that created them change. Some clouds last only minutes, while others can persist for days, slowly changing shape as they drift across the sky. Orographic lifting creates some of the most predictable cloud formations. When moving air encounters a mountain range, it has no choice but to rise up and over the obstacle. As it rises, it cools, and if it contains enough moisture, clouds form along the windward side of the mountains. This is why mountain ranges often have clouds clinging to their peaks, like gentle caps of white cotton. The size of cloud droplets plays a crucial role in how clouds behave. Most cloud droplets are remarkably uniform in size within any given cloud, but they can grow through collision and coalescence. When droplets bump into each other in the turbulent air within a cloud, they sometimes stick together, forming slightly larger droplets. This process happens very slowly at first, but as droplets grow larger, they fall faster and collide with more droplets below them. Temperature inversions create some of the most interesting cloud behaviors. Normally, air gets cooler as you go higher, but sometimes a layer of warm air sits on top of cooler air near the surface. This acts like a lid, trapping moisture below and creating low-hanging clouds or fog that can persist for hours or even days. Fog is simply a cloud that has formed at ground level. It occurs when the air near the surface becomes saturated with moisture and cools to its dew point. Radiation fog forms on clear, calm nights when the ground cools rapidly. Advection fog develops when warm, moist air moves over a cooler surface, like when warm air flows over cold water or snow-covered ground. The different shapes and structures of clouds tell us stories about the atmospheric conditions that created them. Lenticular clouds, those smooth, lens-shaped formations, form when air flows over mountains in stable layers. They look almost otherworldly, like flying saucers, because they maintain their shape even as air continuously flows through them. Mammatus clouds hang from the sky like soft pouches or bubbles, creating an upside-down landscape of gentle curves. They form when dense, cold air within a cloud sinks down into warmer air below, creating these distinctive bulging formations that can cover the entire visible sky with their regular patterns. Cloud streets are long, parallel lines of cumulus clouds that form when cold air flows over warmer water. The contrast in temperature creates regular circulation patterns that organize the clouds into these neat rows, like nature's own perfectly planned city streets in the sky. The process of cloud seeding demonstrates how delicate the balance of cloud formation really is. By introducing additional condensation nuclei into existing clouds, scientists can sometimes encourage precipitation. Silver iodide crystals, which have a structure similar to ice, can provide extra nucleation sites for ice crystal formation in supercooled clouds. Supercooled water droplets exist in a fascinating state of being amidst liquid water at temperatures well below freezing. In clouds, water droplets can remain liquid at temperatures as low as -40 degrees Celsius. They exist in this precarious state until something triggers their immediate freezing, like contact with an ice crystal or particle. The colors we see in clouds come from the way water droplets and ice crystals interact with sunlight. White clouds appear white because their droplets are large enough to scatter all colors of light equally. Gray clouds look gray because they're either very thick, blocking much of the sunlight from reaching us, or because they're backlit by the sun. Iridescence in clouds creates some of nature's most subtle and beautiful displays. When sunlight passes through very small uniform water droplets or ice crystals, it diffracts and creates patches of soft color minus gentle greens, pinks, and blues that shimmer at the edges of clouds. This phenomenon is most visible in thin clouds near the sun, though you should never look directly at the sun to observe it. The weight of clouds is both surprising and reassuring. A typical cumulus cloud, looking light and fluffy from below, actually contains hundreds of tons of water. Yet this massive weight is distributed across such a large volume and consists of such tiny droplets that the whole mass floats effortlessly in the sky. Convection plays a fundamental role in cloud development. When the sun heats the ground, it warms the air directly above it. This warm air becomes less dense than the cooler air around it and begins to rise in invisible bubbles or columns called thermals. Glider pilots and soaring birds use these thermals to gain altitude, riding the same invisible elevators that create cumulus clouds. The daily cycle of cloud formation follows the rhythm of solar heating. On clear days, cumulus clouds often begin forming late in the morning as the sun warms the ground enough to create strong thermals. They typically reach their peak development in the afternoon when heating is strongest, then begin to dissipate in the evening as the sun's warmth diminishes. Wind shear, the change in wind speed and direction with altitude, sculpts clouds into various shapes. Strong wind shear can stretch and distort clouds, creating the anvil tops of thunderstorms or the wispy trails that stream from mountain peaks. Gentle wind shear creates smooth, layered clouds that spread horizontally across the sky. The concept of cloud base is beautifully consistent. In any given area, cumulus clouds tend to form at approximately the same altitude because they all form when rising air reaches its dew point. This creates the familiar sight of puffy clouds all sitting at the same level in the sky, like a fleet of white ships floating on an invisible sea. Atmospheric rivers transport moisture across vast distances, creating cloud systems thousands of miles long. These narrow corridors of concentrated water vapor can carry moisture from tropical oceans to distant continents, feeding the cloud systems that bring rain and snow to regions far from any ocean. The formation of ice crystals within clouds follows beautiful geometric patterns. Each ice crystal grows in a unique hexagonal pattern based on the temperature and humidity conditions it encounters. The intricate branching patterns of snowflakes reflect the journey each crystal took through different layers of the atmosphere as it grew within its parent cloud. Sublimation, the direct transformation from ice to water vapor without melting, plays an important role in cloud dynamics. High-altitude clouds made of ice crystals can disappear through sublimation when the air around them becomes dry, even if temperatures remain well below freezing. The ice crystals simply vanish back into invisible water vapor. Cloud condensation nuclei come from sources both local and incredibly distant. Salt particles from ocean spray can travel hundreds of miles inland. Dust from the Sahara Desert regularly crosses the Atlantic Ocean to seed clouds in the Amazon rainforest. Even particles from volcanic eruptions can circle the globe multiple times, serving as condensation nuclei for clouds far from their origin. The greenhouse effect of clouds is complex and fascinating. Low, thick clouds generally cool the Earth by reflecting sunlight back to space. High, thin clouds often warm the planet by allowing sunlight through but trapping heat radiating back from Earth's surface. The net effect depends on the altitude, thickness, and droplet size of the clouds. Mesocyclones are rotating updrafts within large thunderstorm clouds that can create some of nature's most dramatic displays. These spinning columns of air, typically 10 to 20 kilometers in diameter, rotate slowly and majestically within supercell thunderstorms. Most remain invisible, marked only by the rotation of the cloud structure around them. Cloud droplets grow through collision and coalescence in a process that's surprisingly inefficient. Most collisions between droplets don't result in coalescence. The droplets simply bounce off each other and continue on their separate paths. Only when size differences and collision angles are just right do droplets merge to form larger drops. The Bergeron-Findeisen process describes how ice crystals in mixed-phase clouds grow at the expense of supercooled water droplets. Ice crystals have a lower vapor pressure than liquid water at the same temperature, so water vapor preferentially deposits on ice crystals, causing them to grow while nearby water droplets shrink and eventually evaporate. Fall streaks, also called virga, are visible trails of precipitation that evaporate before reaching the ground. These ghostly streamers hanging from clouds show us precipitation in the process of formation and dissipation, like nature's own time-lapse photography of the water cycle. The electric charges that develop within clouds create some of the most dramatic phenomena in our atmosphere. As ice crystals and supercooled droplets collide within thunderclouds, they exchange electrical charges. Typically, smaller particles become positively charged and rise to the top of the cloud, while larger particles become negatively charged and sink toward the bottom. Lapse rates describe how temperature changes with altitude, and they're crucial for understanding cloud formation. The dry adiabatic lapse rate describes how quickly dry air cools as it rises minus about 10 degrees Celsius per kilometer. The moist adiabatic lapse rate is lower, about 6 degrees per kilometer, because condensing water vapor releases heat that partially offsets the cooling. Kelvin-Helmholtz clouds create some of the most distinctive wave patterns in the sky. These formations look like breaking ocean waves and occur when there's a significant difference in wind speeds between two layers of air. The faster-moving upper layer creates rolling vortices along the boundary, resulting in clouds that look like a series of curling waves frozen in mid-break. The hygroscopic properties of condensation nuclei affect how easily clouds form. Salt particles are particularly effective condensation nuclei because they're hygroscopic minus. They naturally absorb water from the air around them. This is why clouds often form more readily over oceans and coastal areas where salt particles are abundant in the atmosphere. Stratocumulus clouds demonstrate the beautiful complexity that can arise from simple processes. These low grey clouds form in layers, but also show individual cloud elements, creating a pattern that looks like a vast grey blanket with a subtle texture. They often form when a layer of moist air is mixed by gentle turbulence, creating just enough variation to produce individual cloud elements within the larger layer. The concept of cloud seeding with electromagnetic fields is an emerging area of research. Some scientists are investigating whether radio waves or other electromagnetic radiation could influence the electrical properties of cloud droplets and potentially affect precipitation formation. While still experimental, this research opens intriguing possibilities for future weather modification. Polar stratospheric clouds form only in the extremely cold conditions of the polar stratosphere, at altitudes between 15 and 25 kilometers. These rare, beautiful clouds play a crucial role in ozone depletion chemistry, and create some of the most spectacular optical displays in polar skies, with brilliant iridescent colors that can be seen even in the dim polar twilight. The urban heat island effect influences cloud formation over cities in fascinating ways. Cities generate heat and moisture through human activities, and the rough urban surface creates more turbulence than smooth rural areas. This combination often leads to increased cloud formation over and downwind of major cities, creating their own local weather patterns. Asperitas clouds, one of the newest officially recognized cloud types, look like ocean waves viewed from underwater. These dramatic undulating formations were only classified in 2017, despite being photographed by cloud enthusiasts for decades. They typically form along the underside of cumulonimbus or stratocumulus clouds, and create some of the most otherworldly sky displays. The role of cosmic rays in cloud formation is an active area of research. Some scientists hypothesize that high-energy particles from space could influence cloud formation by ionizing air molecules and creating additional condensation nuclei. While the effect appears to be small, it suggests connections between clouds and phenomena occurring far beyond our planet. Gravity waves in the atmosphere create beautiful regular patterns in cloud formations. These waves aren't related to gravitational waves from space, but rather to the wave-like motion of air masses responding to buoyancy forces. When these atmospheric gravity waves interact with cloud layers, they create regular patterns of thick and thin areas that can extend for hundreds of kilometers. The fractal nature of clouds reveals the mathematical beauty underlying natural processes. Cloud boundaries, when examined at different scales, show similar patterns of complexity, whether viewed from space, from an airplane, or from the ground. This self-similar structure reflects the turbulent processes that shape cloud development across all scales. Pyrocumulus clouds form above intense heat sources like forest fires or volcanic eruptions. The extreme heating creates powerful updrafts that can punch through normal atmospheric layers, carrying smoke, ash, and moisture high into the atmosphere. These clouds can develop into full thunderstorms, sometimes producing lightning that can start additional fires. The role of vegetation in cloud formation through transpiration connects the living earth with the sky above. Plants release water vapor through their leaves in a process that can contribute significantly to local humidity. The Amazon rainforest, for example, generates much of its own rainfall through this biological recycling of water between forest and atmosphere. Cloud streets that form over large bodies of water create some of the most regular and beautiful patterns visible from space. Cold air moving over relatively warm water creates parallel lines of convection, which organize into long rows of cumulus clouds. These cloud streets can extend for hundreds of kilometers and maintain their regular spacing with remarkable consistency. The persistence of contrails from aircraft depends on atmospheric conditions in ways that mirror natural cloud formation. In humid conditions at flight altitudes, the water vapor and particles from jet engines provide enough condensation nuclei and moisture to create clouds that can persist for hours and spread to cover large areas of sky. Altocumulus lenticularis clouds that form over mountains can remain stationary for hours, even though strong winds are constantly flowing through them. These lens-shaped clouds mark the peaks of atmospheric waves, remaining fixed in position like rocks in a stream while air continuously flows through them. They serve as visible markers of powerful invisible forces in the atmosphere. The diurnal cycle of cloud formation creates a rhythm that's both predictable and endlessly variable. Morning often brings fog and low stratus clouds as cool night air meets warming surfaces. Afternoon typically sees the development of cumulus clouds as solar heating creates thermals. Evening may bring the dissipation of daytime clouds as cooling reduces convection, but it can also trigger the formation of different cloud types as the atmosphere stabilizes. Supercell thunderstorms represent clouds at their most organized and powerful. These rare storms develop their own mesocyclone minus a rotating updraft that can persist for hours. The updraft in a supercell can reach speeds of 100 miles per hour or more, creating a cloud structure so tall it sometimes pushes against the tropopause, the boundary between the troposphere and stratosphere. The anvil shape of mature thunderstorm clouds tells a story of atmospheric layers. As the powerful updraft in a thunderstorm carries air high into the atmosphere, it eventually encounters the tropopause minus a stable layer, where temperature stops decreasing with altitude. Unable to penetrate this barrier, the ascending air spreads horizontally, creating the characteristic anvil shape that can extend for hundreds of kilometers downwind. Noctilucent clouds form at the edge of space, about 80 kilometers above Earth's surface in the mesosphere. These silvery blue clouds are only visible during deep twilight and consist of ice crystals formed around meteoric dust particles. They're most commonly seen at high latitudes during summer months and may be becoming more common due to increasing atmospheric moisture and cooling in the upper atmosphere. The autoconversion process describes how cloud droplets transition from the stable suspended state to precipitation-sized drops. This critical threshold typically occurs when droplets reach a diameter of about 40 micrometers. Once droplets exceed this size, they begin to fall fast enough to efficiently collect smaller droplets in their path, rapidly growing into raindrops. Cloud top temperatures, measured by satellite, provide crucial information about cloud height and structure. Infrared sensors detect the temperature of cloud tops, and since temperature decreases predictably with altitude, scientists can calculate cloud heights across the globe. The coldest cloud tops indicate the tallest clouds, often associated with severe weather. The role of aerosols from human activities in cloud formation is complex and still being studied. Pollution particles can serve as additional condensation nuclei, potentially increasing cloud droplet numbers while decreasing their average size. This can make clouds more reflective, but also potentially affect their ability to produce precipitation. Mixed-phase clouds containing both water droplets and ice crystals exist in a delicate balance. These clouds typically form at temperatures between 0 and -40 degrees Celsius, where water can exist in both liquid and solid phases. The interaction between the two phases creates complex dynamics that influence precipitation formation and cloud evolution. The concept of cloud seeding efficiency varies dramatically with atmospheric conditions. In some cases, adding condensation nuclei to existing clouds can increase precipitation by 10 to 20%. In other conditions, seeding may have no measurable effect. The success depends on factors like droplet size distribution, ice crystal concentration, and the natural precipitation processes already occurring within the cloud. Shelf clouds form along the leading edge of thunderstorm downdrafts, creating dramatic horizontal clouds that seem to roll across the landscape. These Arcus clouds mark the boundary between cool, dense air flowing out from a thunderstorm and the warm air ahead of it. They can extend for many kilometers and create some of the most photogenic cloud formations. The role of sea surface temperature in cloud formation creates feedback loops that influence global climate patterns. Warmer oceans provide more water vapor for cloud formation, but they also change atmospheric circulation patterns that affect where and how clouds develop. These complex interactions are crucial components of Earth's climate system. Wall clouds represent one of the most ominous cloud formations, indicating strong rotation within a supercell thunderstorm. These lowered areas of cloud base form where the mesocyclone within the storm creates an area of reduced pressure, causing cloud base to lower toward the ground. While not all wall clouds produce tornadoes, they indicate the potential for severe weather. Fractus clouds are the ragged, torn-looking cloud fragments that often form during stormy weather. These scud clouds develop when strong winds and turbulence break apart larger cloud formations, or when humid air is rapidly lifted and cooled in the chaotic atmosphere around thunderstorms. The optical depth of clouds determines how much sunlight they block and reflects. Thin clouds with low optical depth allow most sunlight through while adding a slight haze to the sky. Thick clouds with high optical depth can block virtually all direct sunlight, creating the grey overcast conditions we associate with heavy cloud cover. Bow echoes in radar imagery show the signature of powerful downdrafts within squall lines, organized lines of thunderstorms. These bow-shaped patterns in precipitation intensity mark areas where strong winds are descending from the storm and spreading out at ground level, sometimes producing damaging straight-line winds over large areas. The role of upper-level divergence in cloud development demonstrates the three-dimensional nature of atmospheric dynamics. When air spreads apart in the upper levels of the atmosphere, it creates an area of reduced pressure that encourages air to rise from below. This upper-level divergence is often the key to explosive thunderstorm development. Pileus clouds form as smooth caps over rising cumulus clouds, creating some of the most elegant cloud formations. These accessory clouds develop when existing stable air is forced upward by a growing cumulus cloud below. As this stable air reaches its condensation level, it forms a smooth, lens-shaped cloud that sits atop the more turbulent cumulus formation. The microphysics of cloud droplet formation involves quantum mechanical effects at the molecular level. The initial clustering of water molecules around condensation nuclei involves subtle energy states and probability distributions that echo throughout the macroscopic world of weather and climate. Cap clouds that form over isolated peaks demonstrate orographic lifting in its purest form. These stationary lenticular clouds form when moist air is forced up and over mountain peaks, cooling to its dew point at the summit. The cloud appears to be sitting on the mountain like a cap, but it's actually air continuously flowing through a stationary wave pattern. The concept of equivalent potential temperature helps meteorologists understand atmospheric stability and cloud formation potential. This parameter combines temperature, moisture, and pressure into a single value that remains constant as air moves up or down in the atmosphere, making it invaluable for predicting where clouds will form. Morning glory clouds are rare roll clouds that can extend for hundreds of kilometers across northern Australia. These solitary wave clouds form under very specific conditions involving sea breezes, land heating, and atmospheric layering. They move across the landscape like slow-motion tsunamis in the sky, creating one of meteorology's most spectacular phenomena. The role of downdrafts in thunderstorm evolution shows how clouds create their own weather patterns. As precipitation forms within a thundercloud and begins to fall, it drags air down with it, creating powerful downdrafts that spread out at ground level. These downdrafts can trigger new thunderstorm development as they force warm, moist air aloft along their edges. Undulatus asperatus. Clouds create formations that look like rough seas viewed from below. These rare clouds form when atmospheric gravity waves interact with cloud layers, creating a rolling, turbulent appearance that can cover the entire visible sky. The dramatic undulations can persist for hours, creating an otherworldly landscape overhead. The efficiency of precipitation formation in different cloud types varies dramatically based on their structure and composition. Warm clouds in tropical regions rely on collision and coalescence of water droplets, while cold clouds use the ice crystal process. Mixed-phase clouds can use both processes, often making them the most effective precipitation producers. Virga, or full streaks, demonstrate the three-dimensional nature of precipitation processes. These visible shafts of rain or snow that evaporate before reaching the ground show us precipitation in various stages of formation and dissipation, creating ethereal curtains hanging from cloud bases. The role of entrainment in cumulus cloud development affects their growth and persistence. As cumulus clouds grow vertically, they mix with the drier air around them along their edges. This entrainment of dry air can limit cloud growth or even cause dissipation depending on the moisture content of the surrounding air. Banner clouds that stream from mountain peaks like flags in the wind form through a combination of orographic lifting and lee wave effects. As wind flows around isolated peaks, it creates areas of reduced pressure on the downwind side, encouraging cloud formation that streams away from the mountain like a banner. The concept of cloud radar allows meteorologists to see inside clouds and study their structure in real time. These specialized radars can detect tiny cloud droplets and ice crystals, revealing the internal architecture of clouds and the processes occurring within them that are invisible to our eyes. Full-streak holes, also called hole-punch clouds, create dramatic circular or elliptical gaps in cloud layers. These form when supercooled water droplets in a thin cloud layer suddenly freeze, creating a chain reaction that clears a large area of cloud. Aircraft passing through such layers can trigger this process, creating perfectly circular holes that can persist for hours. The role of boundary layer dynamics in cloud streak formation demonstrates how surface conditions influence cloud patterns. Regular heating patterns on the ground create organized convection that aligns into parallel rows, forming the cloud streaks that are so prominent in satellite imagery over oceans and large lakes. Stratospheric polar vortex interactions can influence cloud formation patterns across entire hemispheres. When this large-scale circulation pattern weakens or shifts, it can alter the paths of storm systems and cloud formations across vast areas, demonstrating the interconnected nature of atmospheric phenomena from local to global scales. Cloud microphysics reveals the intimate details of how individual droplets behave within the larger cloud system. Each droplet exists in a delicate balance between growth and evaporation, constantly exchanging water molecules with the surrounding air. The surface tension of these tiny spheres creates a curved interface that affects vapor pressure, making smaller droplets more prone to evaporation than larger ones. The concept of critical droplet size explains why some clouds dissipate while others grow into towering formations. Droplets smaller than about 2 micrometers in radius tend to evaporate quickly, while those larger than this critical size can continue to grow through condensation. This size threshold acts like a gateway between the invisible vapor phase and the visible cloud phase. Brownian motion affects the smallest cloud droplets, causing them to jiggle and dance randomly as air molecules bombard them from all directions. This molecular scale movement becomes significant for the tiniest droplets, adding another layer of complexity to their behavior within the cloud environment. The role of atmospheric tides in cloud formation follows cycles as regular as ocean tides but driven by solar heating rather than gravitational forces. These subtle pressure oscillations, with periods of 12 and 24 hours, can influence the timing and location of cloud development, especially in tropical regions where other atmospheric forces are weaker. Ice multiplication processes within clouds can dramatically increase ice crystal concentrations through several fascinating mechanisms. The Hallett-Mossop process occurs when supercooled droplets collide with ice crystals at temperatures between -3 and -8 degrees Celsius, causing tiny ice splinters to break off and create new ice crystals. Cloud electrification involves complex interactions between ice crystals, supercooled droplets, and Grapel Mesa soft hail pellets within thunderclouds. As these particles collide and interact, they exchange electrical charges in ways that depend on temperature, collision velocity, and the presence of chemical impurities. This process can build up enormous electrical potential differences within a single cloud. The role of atmospheric rivers in global moisture transport demonstrates how clouds and weather systems are connected across ocean basins. These narrow corridors of enhanced water vapor transport can carry moisture equivalent to multiple Mississippi rivers from tropical oceans to distant continents, feeding the cloud systems that bring precipitation to regions thousands of miles away. Kelvin waves in the atmosphere create cloud patterns that propagate around the globe along the equator. These large-scale atmospheric disturbances related to the waves that travel along ocean thermoclines can influence cloud formation and precipitation patterns across the entire tropical belt, connecting weather events in Africa with those in South America and the Pacific. The interaction between clouds and cosmic radiation involves subtle but potentially important effects on climate. Galactic cosmic rays can create ionization in the atmosphere that may influence cloud droplet formation, though the magnitude of this effect remains a subject of active research. The connection suggests that Earth's climate system may be influenced by events occurring in distant regions of our galaxy. Supercooled water in clouds can exist at temperatures as low as -40 degrees Celsius before spontaneously freezing. This metastable state requires perfectly pure water and the absence of ice-nucleating particles. In this supercooled state, water droplets exist in a fascinating liminal space between liquid and solid phases. The role of volcanic ash in cloud formation can persist for years after major eruptions. Sulfur dioxide from volcanic eruptions combines with water vapor in the stratosphere to form sulfuric acid droplets that can serve as cloud condensation nuclei. These volcanic aerosols can influence cloud properties and climate patterns long after the original eruption. Atmospheric gravity waves generated by thunderstorms can propagate for hundreds of kilometers, triggering new cloud formation far from the original storm. These waves travel through the atmosphere like ripples on a pond, carrying energy and momentum that can initiate convection in areas where conditions are nearly but not quite favorable for cloud development. The concept of liquid water path describes the total amount of liquid water in a vertical column through a cloud. This parameter, measurable by satellite instruments, provides crucial information about cloud thickness and precipitation potential. Clouds with high liquid water paths are more likely to produce precipitation and have different radiative properties than thinner clouds. Cloud droplet size distributions follow mathematical patterns that reveal the underlying physical processes. In most clouds, droplet sizes cluster around a characteristic value with a predictable spread. The shape of this distribution tells meteorologists about the age of the cloud, the efficiency of collision processes, and the likelihood of precipitation formation. The role of sea salt particles as cloud condensation nuclei creates a direct connection between ocean waves and cloud formation. When waves break, they inject tiny salt particles into the atmosphere that can travel thousands of kilometers inland, serving as highly effective condensation nuclei that influence cloud properties far from any ocean. Homogeneous nucleation of ice crystals occurs only under extremely pure conditions where water freezes spontaneously at temperatures below -40 degrees Celsius. This process requires no foreign particles and demonstrates the remarkable ability of pure water to exist in a supercooled state. In nature, heterogeneous nucleation on particles is far more common. The Bergeron-Findeisen process efficiency depends on the delicate balance between ice crystals and supercooled droplets within mixed-phase clouds. When this balance is optimal, ice crystals can grow rapidly at the expense of surrounding water droplets, leading to precipitation formation. The process is most efficient at temperatures between -10 and -20 degrees Celsius. Cloud top entrainment describes how dry air from above mixes into the upper portions of growing cumulus clouds. This process can significantly affect cloud development, sometimes causing the upper portions of clouds to evaporate even as the base continues to be fed by rising thermals. The rate of entrainment depends on wind shear and atmospheric stability. The role of dust particles from distant deserts in cloud formation creates connections between seemingly unrelated regions of Earth. Saharan dust regularly crosses the Atlantic Ocean to influence cloud formation in the Caribbean and Amazon basin. Similarly, dust from Asian deserts can travel across the Pacific to affect weather patterns in North America. Mammatus cloud formation requires very specific atmospheric conditions involving dense, cold air within a cloud sinking into warmer air below. The resulting convective instability creates the characteristic pouch-like protrusions that hang from the cloud base like a three-dimensional honeycomb pattern across the sky. The concept of cloud lifetime encompasses the entire evolution from initial formation to final dissipation. Some clouds exist for only minutes, forming and evaporating as local conditions fluctuate. Others, particularly large stratiform systems, can persist for days as they slowly evolve and move across continents. Aerosol cloud interactions represent one of the most complex aspects of cloud physics. Different types of aerosol particles affect clouds in different ways. Some serve as efficient condensation nuclei. Others absorb radiation and heat the surrounding air, and still others provide surfaces for chemical reactions that affect cloud properties. The role of atmospheric stability in determining cloud types follows patterns that meteorologists use to forecast weather. Stable atmospheres tend to produce layered, stratiform clouds that spread horizontally. Unstable atmospheres favor vertical cloud development, leading to the towering cumulus and cumulonimbus formations associated with convective weather. Cloud streets that form parallel to the wind direction demonstrate the organized nature of atmospheric convection. These regularly spaced lines of cumulus clouds mark the locations of convective rolls, organized circulation patterns that develop when cold air flows over a warmer surface. The spacing between cloud streets relates to the depth of the convective layer. The dielectric properties of cloud droplets affect how they interact with radar and microwave radiation. Pure water droplets have specific electrical characteristics that change with temperature and droplet size. These properties allow meteorologists to use radar to study cloud internal structure and distinguish between different types of precipitation particles. Ice crystal habits. The shapes that ice crystals take as they grow depend sensitively on temperature and humidity conditions. Plates form at certain temperatures, columns at others, and complex branch structures like dendrites develop under specific combinations of temperature and supersaturation. Each crystal's shape tells the story of its journey through different atmospheric layers. The role of cloud feedback in climate change involves complex interactions between warming temperatures, cloud properties, and radiation balance. As the atmosphere warms, cloud heights may increase, cloud droplet sizes may change, and cloud coverage patterns may shift. These changes can either amplify or moderate the warming, making cloud feedback one of the largest uncertainties in climate predictions. Pyrocumulonimbus clouds represent some of the most extreme atmospheric phenomena, forming above intense wildfires and generating their own weather systems. These fire-generated thunderstorms can produce lightning that starts additional fires, create their own wind patterns, and inject smoke and particles high into the stratosphere where they can persist for months. The concept of precipitable water describes the total amount of water vapor in a vertical column of atmosphere. This parameter, measurable by radio sondes and satellites, indicates the moisture available for cloud formation and precipitation. High precipitable water values suggest the potential for significant precipitation if lifting mechanisms are present. Orographic precipitation patterns demonstrate how topography shapes regional climate through cloud formation processes. Windward slopes of mountain ranges receive enhanced precipitation as rising air cools and condenses, while leeward slopes often experience rain shadows. The role of atmospheric layering in cloud formation creates the complex vertical structure we see in many weather systems. Different layers of the atmosphere can have different temperatures, humidities, and wind patterns, leading to multiple cloud decks at various altitudes. These layered systems can interact in complex ways, with upper-level clouds affecting the development of lower-level formations. Cloud droplet activation describes the process by which water vapor begins to condense on aerosol particles. Not all particles can serve as cloud condensation nuclei. They must be large enough and have the right chemical properties to attract water molecules. The efficiency of this process affects how readily clouds form under given atmospheric conditions. The influence of land use patterns on local cloud formation demonstrates the connection between human activities and atmospheric processes. Urban areas, agricultural regions, and forests all affect local temperature and moisture patterns in ways that can influence cloud development. Cities often enhance cloud formation through increased heat and moisture release, while deforestation can reduce local precipitation. Satellite cloud climatology reveals global patterns in cloud formation and evolution that would be impossible to observe from the ground. These space-based observations show how cloud patterns change with seasons, respond to ocean temperature variations, and vary with different climate oscillations like El Niño and La Niña. The role of atmospheric chemistry in cloud formation involves complex interactions between water vapor, aerosol particles, and trace gases. Chemical reactions can occur on the surfaces of cloud droplets and aerosol particles, affecting their ability to serve as condensation nuclei and influencing the properties of the resulting clouds. Convective inhibition describes atmospheric conditions that suppress cloud development despite the presence of moisture and potential instability. This cap of stable air can prevent surface heating from triggering thunderstorm development, leading to clear skies even when conditions seem favorable for convection. When this inhibition is eventually overcome, explosive storm development can occur. The concept of cloud optical thickness quantifies how much solar radiation clouds absorb and scatter. This property depends on cloud droplet size, number concentration, and liquid water content. Clouds with high optical thickness appear very white and bright, while those with low optical thickness appear more translucent. Marine stratocumulus clouds cover vast areas of the world's oceans and play a crucial role in regulating Earth's energy balance. These extensive cloud decks form in the stable marine boundary layer and can persist for days or weeks. Their high reflectivity helps cool the planet by reflecting solar radiation back to space. The role of atmospheric rivers in extreme precipitation events demonstrates how moisture transport patterns can concentrate water vapor over specific regions. When atmospheric rivers encounter mountainous terrain, the forced lifting can produce extreme rainfall rates and flooding, showing how global-scale moisture transport patterns can have very localized impacts. Cloud seeding success rates vary significantly depending on cloud type, atmospheric conditions, and seeding technique. In some cases, seeding can increase precipitation by 10 to 30%, while in other situations it may have no measurable effect. The most successful seeding operations target supercooled clouds with temperatures between -5 and -20 degrees Celsius. The interaction between solar radiation and cloud droplets creates the complex patterns of light and shadow we see on partly cloudy days. As sunlight passes through clouds of varying thickness and droplet concentration, it creates an ever-changing mosaic of bright and dim areas on the ground below. This interplay between clouds and sunlight has inspired artists and poets throughout human history. Nocturnal low-level jets, streams of fast-moving air that develop at night in the lower atmosphere, can transport moisture and influence cloud formation patterns. These jets often strengthen after sunset, when surface cooling creates atmospheric conditions favorable for their development. They can carry moisture from source regions to areas where it feeds into daytime convective development. The role of vegetation feedback in cloud formation creates complex interactions between ecosystems and weather patterns. Forests release moisture through transpiration and affect local wind patterns through their influence on surface roughness and heating. Deforestation can reduce local precipitation, while reforestation may enhance cloud formation and rainfall. Cloud aerosol interactions represent one of the most active areas of atmospheric research. As aerosol concentrations change due to human activities, cloud properties respond in complex ways. Some aerosols suppress precipitation by creating many small droplets, while others may enhance precipitation formation through their ice-nucleating properties. The fractal dimension of cloud boundaries reveals the mathematical beauty underlying turbulent atmospheric processes. Cloud edges show similar complexity patterns at different scales of observation, from satellite images showing continental-scale cloud systems to close-up photographs revealing meter-scale structure. Atmospheric stability parameters help meteorologists assess the potential for different types of cloud development. Indices like CAPE, convective available potential energy, and wind shear measurements provide quantitative measures of atmospheric instability and the likelihood of severe weather development. The role of oceanic upwelling in marine cloud formation demonstrates the connection between ocean circulation and atmospheric processes. When deep cold water rises to the ocean surface, it cools the overlying air and often leads to the formation of marine layer clouds and fog. These clouds can persist for months during upwelling seasons. Cloud microphysical processes operate on timescales ranging from microseconds to hours. Individual droplet collisions occur in microseconds, droplet growth through condensation happens over minutes, and cloud system evolution unfolds over hours. Understanding these multi-scale processes is crucial for accurate weather prediction. The influence of terrain channeling on cloud formation patterns creates localized weather phenomena in mountainous regions. Valleys can channel moisture-laden air into specific areas, creating preferred locations for cloud development. These topographic effects can produce microclimates with cloud patterns that differ dramatically from the surrounding region. Radiative cooling at cloud tops creates temperature differences that drive atmospheric circulation patterns. As clouds radiate heat to space, their tops cool rapidly, especially at night. This cooling can strengthen vertical air motions and affect cloud development patterns over timescales of hours to days. The concept of cloud persistence probability helps meteorologists understand how long different types of clouds are likely to last under various atmospheric conditions. Some cloud types are inherently transient, while others can maintain themselves for extended periods through feedback processes that reinforce their existence. Atmospheric turbulence within clouds creates complex mixing patterns that affect droplet growth and cloud structure. Different scales of turbulence, minus from large eddies spanning kilometers to small-scale mixing at the centimeter scale, all contribute to the internal dynamics of clouds and their evolution over time. The role of gravity wave breaking in cloud formation can trigger convection in unexpected locations. When atmospheric gravity waves encounter stable layers or wind shear, they can break like ocean waves, creating localized areas of turbulence and mixing that may initiate cloud development. Cloud droplet collision efficiency depends on the relative sizes of the droplets involved. When droplets of similar size collide, they often bounce off each other without merging. However, when larger droplets collide with much smaller ones, collection efficiency increases dramatically, leading to rapid droplet growth through the collision coalescence process. The seasonal cycle of cloud formation patterns reflects the changing balance of atmospheric energy as Earth orbits the Sun. Summer typically brings more convective cloud development as solar heating creates strong thermals, while winter often features more stratiform clouds associated with large-scale weather systems. Mesoscale convective systems represent organized arrangements of thunderstorms that can persist for many hours and cover areas the size of entire states. These systems develop their own circulation patterns and can maintain themselves through complex feedback processes between the individual storm cells and the larger-scale environment. The role of atmospheric moisture recycling demonstrates how water evaporated from one region can contribute to precipitation in distant areas. A molecule of water may evaporate from the ocean, fall as rain over land, evaporate again from soil or vegetation, and continue this cycle multiple times as weather systems transport it across continents. Cloud radar technology allows scientists to peer inside clouds and observe their internal structure with unprecedented detail. These specialized instruments can detect individual precipitation particles and track their motion within clouds, revealing the complex three-dimensional structure of cloud systems. The influence of climate oscillations like the El Niño Southern Oscillation on global cloud patterns demonstrates the interconnected nature of Earth's climate system. Changes in ocean temperatures in the tropical Pacific can alter atmospheric circulation patterns that affect cloud formation and precipitation across the globe. Iridescent clouds create some of nature's most subtle and beautiful optical displays through the diffraction of sunlight by very small uniform water droplets or ice crystals. These colors are most vivid in thin clouds near the sun and can produce ethereal greens, pinks, and blues that shimmer and change as you watch. The role of boundary layer thermals in cumulus cloud formation follows a daily cycle that reflects the rhythm of solar heating. Morning brings weak thermals that may produce only small cumulus clouds. Afternoon sees the strongest thermal development and the largest cumulus formations. Evening brings weakening thermals and often cloud dissipation. Supercooled water droplet concentrations in winter clouds can exceed several hundred per cubic centimeter, creating conditions ripe for rapid ice crystal growth when ice nucleation occurs. These high concentrations of metastable liquid water represent enormous amounts of energy that can be rapidly released during freezing processes. The concept of cloud-based convergence describes how air flows into the bottom of cumulus clouds from surrounding areas. This convergence creates the updrafts that feed cloud growth and can often be detected by the pattern of surface winds around developing cumulus clouds. Atmospheric instability indices combine measurements of temperature, humidity, and wind to create single numbers that summarize the potential for thunderstorm development. These indices, with names like SWET and K-index, help forecasters quickly assess severe weather potential across large geographic areas. The role of ice crystal habits in precipitation formation demonstrates how the microscopic structure of ice affects macroscopic weather phenomena. Stellar dendrites are efficient at collecting supercooled droplets, while simple plates may fall slowly and evaporate before reaching the ground. The type of ice crystals that form depends on precise temperature and humidity conditions. Cloud chamber experiments in laboratories help scientists understand the fundamental processes of droplet formation and growth under controlled conditions. These studies reveal details about nucleation processes, droplet interactions, and ice formation that would be impossible to observe in natural clouds. The influence of atmospheric pressure patterns on cloud formation extends from local effects to planetary-scale circulation systems. High-pressure areas typically suppress cloud formation through subsidence, while low-pressure systems encourage rising motion and cloud development. These pressure patterns are driven by the uneven heating of Earth's surface and the planet's rotation. Convective available potential energy represents the amount of energy available for vertical motion in unstable atmospheric conditions. High Kate values indicate the potential for strong thunderstorm development, while low values suggest that any convection will be weak. This energy comes from the buoyancy of warm, moist air parcels compared to their environment. The role of atmospheric layering in creating different cloud types demonstrates how vertical atmospheric structure controls cloud formation. Shallow layers may produce only low stratus clouds, while deep layers with strong instability can support towering cumulonimbus development that reaches the tropopause. Cloud droplet evaporation rates depend on the humidity of the surrounding air and the size of the droplets. In dry air, small droplets can evaporate completely in seconds, while larger droplets may persist for minutes. This size-dependent evaporation is one reason why cloud droplets tend to grow toward a characteristic size distribution. The influence of surface albedo on local cloud formation creates feedback loops between ground conditions and atmospheric processes. Dark surfaces absorb more solar radiation and create stronger thermals that favor cumulus cloud development. Light surfaces reflect more radiation and may suppress local convection. Atmospheric moisture flux convergence identifies areas where water vapor is being concentrated by wind patterns. These convergence zones often mark preferred locations for cloud development and precipitation, making them important features for weather forecasters to identify and track. As we continue our gentle exploration of the world above us, consider how each of these processes contributes to the endless variety and beauty of cloud formations. From the quantum mechanical interactions that govern initial droplet formation to the planetary scale circulation patterns that organize weather systems, clouds represent a perfect marriage of the infinitely small and the magnificently large. The atmosphere above us is never truly at rest. Even on the stillest days, invisible processes of evaporation, condensation, and air movement continue their eternal dance. Water molecules that evaporated from a distant ocean this morning might become part of a cloud above you this evening, carrying with them the memory of their journey across land and sea. Each cloud formation tells a story not just of present conditions but of the atmospheric history that led to its creation. The height of its base speaks of the stability of the air below. The shape of its top reveals the nature of the winds aloft. The texture of its edges shows the turbulence within. Learning to read these stories transforms every sky into a fascinating book written in the language of physics and meteorology. The water cycle that creates our clouds connects every drop of water on Earth in an endless circulation that has continued for billions of years. The water molecules in today's clouds have fallen as rain on ancient forests, flowed in prehistoric rivers, and evaporated from long-vanished seas. They carry within them the history of our planet's climate, a history that continues to unfold in the skies above us. Modern technology has revealed cloud processes that were invisible to earlier generations of scientists. Satellite images show us the grand patterns of cloud formation across entire continents. Radar penetrates inside clouds to reveal their internal structure. Computer models simulate cloud behavior with increasing precision, helping us understand and predict the complex interactions between clouds and climate. Yet, despite all our scientific understanding, clouds retain their capacity to inspire wonder and contemplation. They remind us that we live at the bottom of an ocean of air, subject to forces and processes that dwarf human experience, yet create the gentle patterns we see painted across our daily skies. They connect us to the cosmic processes that govern planetary atmospheres, while providing the immediate tangible beauty that enriches our daily lives. The study of clouds bridges many scientific disciplines. Physics, chemistry, mathematics, and computer science all contribute to our understanding of these atmospheric phenomena. Yet clouds also belong to the realm of art and poetry, inspiring human creativity with their endless variety and ephemeral beauty. As we near the end of our journey through the science of clouds, take a moment to reflect on the remarkable complexity hidden within what appears to be simple vapor suspended in air. Every cloud represents the culmination of countless molecular interactions, atmospheric processes, and energy exchanges that span scales from the quantum to the planetary. The next time you watch clouds drift across the sky, you might marvel at the precision of the physical laws that govern their formation and movement. You might appreciate the delicate balance of forces that keeps them suspended in the air. You might wonder about the journeys of the water molecules within them, or contemplate the vast atmospheric currents that guide their stately progress across the heavens. Clouds remind us that our planet is a dynamic living system, where ocean, land, and atmosphere interact in complex and beautiful ways. They are visible manifestations of the energy from our sun being transformed and redistributed across Earth's surface. They are part of the great thermal engine that drives our weather and shapes our climate. In their formation and dissipation, Clouds embody the principles of impermanence that govern all natural processes. They appear, evolve, and vanish in cycles that range from minutes to days, yet the processes that create them are as constant and reliable as sunrise. They teach us that change and constancy can coexist, that patterns can emerge from apparent chaos, and that beauty can arise from the simplest physical principles. Whether you're watching the first puffy cumulus clouds of a spring morning, the dramatic anvil tops of summer thunderstorms, the gentle grey embrace of winter stratus, or the delicate cirrus wisps of a clear autumn day, you're witnessing one of nature's most accessible and continuous performances. The sky is always available to us, always changing, always beautiful in its endless variety. The science of clouds continues to evolve as we develop better instruments, more sophisticated models, and deeper understanding of atmospheric processes. Each new discovery reveals additional layers of complexity and beauty in these familiar yet mysterious formations that float above us. There are still questions to be answered, processes to be understood, and wonders to be discovered in the seemingly simple act of water vapor condensing in the sky. As we conclude our peaceful exploration of cloud formation and movement, remember that this knowledge doesn't diminish the wonder of clouds' menace, it enhances it. Understanding the intricate processes that create a sunset-illuminated cumulonimbus or the delicate physics behind a morning's dew-touched stratus only adds depth to their beauty. Science and wonder are not opponents but partners in appreciating the magnificent complexity of our natural world. Thank you for joining me on this extended journey through the realm of clouds. I hope these gentle explorations of atmospheric science have provided a soothing companion for your evening, whether you've stayed awake to hear every detail or allowed yourself to drift away on the soft currents of scientific wonder. Sleep well, and may your dreams be filled with the endless dance of water vapor and wind, the gentle rhythm of condensation and evaporation, and the peaceful knowledge that above us, always, the sky continues its ancient and beautiful work of creating clouds. Good night wherever you are in this wide world, and remember that tomorrow's sky will bring new formations, new patterns, and new opportunities to witness the quiet miracles that surround us every day. Sweet dreams, and may you always find wonder in the simple act of looking up. Billions of water molecules are dancing their eternal dance, condensing and evaporating, rising and falling, creating the ever-changing canvas that stretches across our sky. Each cloud tells a story of temperature and pressure, of winds and water, of the delicate balance that makes weather possible on our remarkable planet. The next time you look up at the sky, whether you see puffy cumulus clouds on a summer afternoon, wispy cirrus clouds stretching across a winter sky, or the gentle grey embrace of stratus clouds on an overcast day, you'll know something of the beautiful complexity behind their formation. You'll understand the invisible forces that shaped them, the microscopic processes that created them, and the vast atmospheric currents that guide their stately journey across the heavens. Remember that clouds are never truly the same twice. Each formation is unique, shaped by the specific conditions of its time and place. The cloud you're looking at now has never existed before, and will never exist again in quite the same form. It's a fleeting sculpture carved from water and wind, a temporary masterpiece in the sky's endless gallery. Thank you for joining me on this peaceful exploration of cloud formation and movement. I hope these gentle facts about the sky above us have provided a soothing companion for your evening, whether you're drifting off to sleep or simply taking a moment to contemplate the wonders that surround us every day. Sleep well, and may your dreams be filled with the soft dance of clouds across endless skies. Good night, wherever you are in the world, and remember to look up tomorrow. There will be new stories written in the clouds above you. Sweet dreams.